February 19th, 1943. Sfax, Tunisia. The American star on the hull had been hastily painted over with German crosses, but the name was still visible beneath the fresh markings. WWII. The Sherman tank sat in the port facility, its engine silent after a journey that should have been impossible. 350 kilometers across North African desert, 4.5 days of continuous operation. Not a single mechanical failure. Hauptmann Friedrich Weber of Heavy Panzer Battalion 501 circled the captured M4 Sherman slowly, his notebook already filled with observations that contradicted everything he thought he understood about American industrial capability. This tank, seized intact during the chaotic American retreat at Sidi Bou Zid just days earlier, had been driven across terrain that routinely disabled German vehicles within 50 kilometers. The crew from the reconnaissance unit that delivered it reported something Weber found difficult to accept. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engine never overheated. The transmission never slipped. The final drives maintained consistent power delivery through sand, rock, and steep gradients that would have shredded a Panzer Mark IV's gearbox. Weber had spent the previous 2 years watching German tanks break down with frustrating regularity. Overheated engines on short road marches, transmission failures after minor obstacles, final drive housings that cracked under stress and left 40-ton vehicles immobilized in the middle of battlefields. He had written reports documenting these failures, submitted recommendations for improvements, and watched as the problems persisted through multiple production runs. Now he stood beside an enemy tank that had just completed a journey no German tank could match, and the implications unsettled him more than any combat action he had witnessed. The Army Weapons Office in Berlin had issued explicit orders. This Sherman must reach the testing facility at Kummersdorf intact and operational. German intelligence had been receiving fragmentary reports about American tank production for months. Numbers that seemed impossible. Claims of automotive reliability that contradicted basic engineering assumptions about the necessary trade-offs between durability and performance. Weber had dismissed much of it as exaggeration or Allied propaganda, but this physical vehicle, sitting before him with dust from 350 kilometers of desert travel coating its hull, made those statistics real in ways that numbers on paper never could. As the loading crews prepared to lift the Sherman onto a cargo ship bound for Germany, Weber made one final inspection of the running gear. The tracks showed wear consistent with hard use, but no broken pins, no damaged links, no signs of imminent failure. The road wheels rolled smoothly without binding. The drive sprockets showed no cracks or stress fractures. Everything about this tank suggested it could drive another 350 kilometers without requiring significant maintenance. Weber had never seen a German tank in similar condition after comparable use. The ship departed Sfax on February 21st, steaming north across the Mediterranean towards Sicily and then on to German ports. Below deck, secured in the cargo hold, WWII represented something more dangerous to German confidence than any Allied weapons system. It was proof that American industry had solved problems German engineers were still struggling to understand. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. WWII rolled off the transport rail car bearing the German designation Panzer 259 and license plate WH058941. Test engineers had already stenciled armor thickness measurements across every surface, marking the hull with precise notations for the comprehensive evaluation program ahead. But it was the powertrain examination that would deliver the most troubling revelations. The German Army Proving Ground at Kummersdorf, located 25 kilometers south of Berlin, served as the primary testing facility for both German and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything from track tension to engine compression ratios, documenting their findings in exhaustive technical reports that circulated through Wehrmacht headquarters and armaments ministry offices. The Sherman was about to undergo the most comprehensive automotive examination German engineering could devise, and the results would challenge fundamental assumptions about tank design that had guided German armoured vehicle development since 1939. The initial inspection team consisted of specialists from multiple technical branches. Powertrain engineers examined the transmission and final drives. Metallurgists tested armour samples. Automotive specialists focused on the engine and cooling systems. Every component was photographed from multiple angles, measured with precision instruments, and documented in meticulous detail. What they discovered in those first weeks contradicted everything German tank doctrine had accepted about the necessary compromises between performance and reliability. The transmission immediately caught the attention of senior engineer Hauptmann Dieter Schneider, a powertrain specialist with 15 years of automotive engineering experience. He had designed gear systems for several German tank models and understood the inherent challenges of transmitting 400 horsepower through mechanical linkages while maintaining durability under combat conditions. The Sherman transmission used helical cut gears, what German engineers called herringbone gears, that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with minimal precision requirements during assembly. Schneider ran his fingers across the gear teeth, feeling the smooth engagement surfaces. German tanks employed straight-cut gears that required extremely precise tolerances to function reliably. Any slight misalignment, any minor manufacturing variation, and the gears would bind or wear prematurely. The straight-cut design was theoretically more efficient, transferring slightly more power with less friction loss. But it demanded precision that German factories, increasingly reliant on forced labor and operating under constant Allied bombing, struggled to maintain consistently. The Americans had chosen helical gears that were slightly less efficient but vastly more forgiving of manufacturing variations. The angled teeth engaged gradually rather than all at once, spreading loads and reducing the catastrophic failures that plagued German transmissions. Schneider had proposed similar designs for German tanks in 1941, but the manufacturing difficulties and the need for specialized cutting equipment had led to rejection of the concept. The Americans had apparently been mass-producing such gears by the thousands, installing them in civilian automobiles and trucks long before the war began. The testing program began with basic automotive trials designed to stress every mechanical system under controlled conditions. Engineers drove War Daddy 3 through obstacle courses that replicated battlefield terrain, steep gradients to test low gear pulling power, soft sand to evaluate traction and cooling efficiency, sharp turns to stress the final drives, high-speed runs on packed surfaces to measure maximum sustainable velocity. After each trial, they disassembled key components to examine wear patterns, searching for signs of inadequate lubrication, excessive heat, or design weaknesses that would lead to eventual failure. The results were documented with Germanic thoroughness in reports that grew increasingly detailed as the testing continued through April and into May of 1943. The Sherman performed adequately in every category. It wasn't exceptional in any single measurement. The armor was adequate but not impressive. The gun was effective but not overwhelming. The speed was acceptable but not remarkable. What distinguished this tank from its German counterparts was the one metric German tanks consistently failed: operational endurance without maintenance intervention. After 50 kilometers of mixed terrain operation, German test drivers reported that the transmission shifted smoothly through all 5 forward gears plus reverse. The synchronization in gears 2 through 5 eliminated the need for double clutching that German tank drivers spent weeks learning to master. An ordinary soldier with basic automotive knowledge could operate this tank after minimal training. German transmissions, by contrast, required skilled operators who understood the complex relationship between engine RPM, vehicle speed, and gear selection. Improper shifting could strip gears or crack the transmission housing, requiring factory-level repairs that took vehicles out of service for weeks. After 100 kilometers, the cooling system continued functioning without signs of stress. The Continental R975 radial engine maintained consistent operating temperatures across varying loads and terrain conditions. German tank engines, particularly the Maybach power plants in the Panther and Tiger, required constant monitoring of coolant temperature and careful throttle management to prevent overheating. Drivers who pushed engines too hard on hot days faced catastrophic failures that could weld pistons to cylinder walls. After 200 kilometers, Kummersdorf engineers noted in their reports that the Sherman's final drives showed no unusual wear, no abnormal heat buildup, no signs of the imminent failures that plagued German designs. The Panther tank, Germany's newest and most advanced medium tank design, used final drive systems inherited from the Tiger program. The configuration employed straight-cut gears in housings that proved chronically inadequate for the loads imposed by the 45-ton vehicle. German mechanics across North Africa and on the Eastern Front had filed countless reports of final drive breakdowns that left Panthers abandoned after movements of less than 100 kilometers. The Sherman's final drives, built using the same helical gear principles as the transmission, simply refused to fail under any conditions the test engineers could devise. By late May of 1943, after the Sherman had accumulated over 1,500 kilometers on Kummersdorf's test tracks without requiring any significant maintenance beyond routine oil changes and track adjustments, the test program's conclusions had become unavoidable. Senior engineers compiled their findings into internal reports intended for Wehrmacht technical staff and armaments ministry officials. The documents, classified as secret and distributed only to personnel with appropriate clearances, painted a sobering assessment of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked, despite possessing extensive theoretical knowledge and scientific expertise. Mass production techniques that German precision manufacturing culture dismissed as crude actually produced more reliable vehicles. Interchangeable parts meant that field mechanics could repair the Sherman using basic tools and components from supply depots. German tanks required factory precision work for many repairs, with parts that often needed individual fitting and adjustment, even when supposedly built to identical specifications. The entire American design philosophy prioritized keeping vehicles operational in field conditions rather than achieving theoretical performance maximums that looked impressive in technical specifications but couldn't be maintained under combat stress. This represented a fundamental difference in engineering approach that German designers had never seriously considered. German engineers calculated optimal specifications and then attempted to manufacture components that met those precise requirements. American engineers designed for mass production first, accepting slightly lower theoretical efficiency in exchange for dramatically improved reliability and maintainability. Oberst Heinrich Müller, head of the Kummersdorf Testing Directorate, summarized the situation in a confidential memorandum to the Army Weapons Office dated June 2, 1943. His assessment was blunt in ways that senior officers rarely permitted themselves in official communications. The Sherman M4 tank demonstrates automotive reliability that exceeds any current German tank design by substantial margins. After 1,500 kilometers of intensive testing under conditions designed to induce mechanical failures, this vehicle has required only routine maintenance. Comparable German tanks would have experienced multiple component failures, requiring major repairs or complete powertrain replacement. Müller's report continued with specific technical observations that grew more troubling with each paragraph. The transmission design using helical cut gears provides durability we cannot currently replicate in mass production. The synchronized shifting mechanism requires no specialized driver training. The cooling system functions reliably under sustained high-load operation. The final drives show no signs of the premature failures that plague our Panther and Tiger programs. Most significantly, American industry manufactures these components in quantities that suggest they have solved production challenges our factories continue to struggle with despite our best efforts. The report's conclusion acknowledged what many senior German officers had been reluctant to face directly. American industrial capacity was not simply larger in scale than German production. It was fundamentally more mature in its approach to mass manufacturing, with decades of civilian automotive experience that Germany had never developed. Before the war, the United States had widespread automobile ownership. Vehicles were commonplace among ordinary citizens across all economic classes. This created an industrial base with extensive experience in building reliable mechanical systems that non-specialist users could operate and maintain. Germany, by contrast, had far more limited civilian automotive experience. Cars remained luxury items for the wealthy and party elite. The Volkswagen program, promised to German workers since 1934, had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in automotive industry maturity translated directly into tank design philosophy in ways that couldn't be overcome through engineering cleverness or scientific knowledge alone. June 6 and 7, 1943. Hillersleben, Artillery Range. Reich Minister Albert Speer arrived to observe a major armament conference attended by leaders from the armaments industry and senior Wehrmacht officers. The demonstration program included hill-climbing trials comparing German and captured Allied tanks. War Daddy 3 sat alongside Germany's latest designs, a Panzer Ausführung D tank fresh from the MAN production facility, a Ferdinand tank destroyer representing Germany's most advanced armoured fighting vehicle technology. The massive Porsche-designed assault gun mounted an 88mm gun on a chassis that weighed 65 tons. Speer, personally responsible to Hitler for armament production and industrial output, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers that neither Speer nor German tank designers particularly wanted to acknowledge, but which the testing data made impossible to ignore. The Sherman climbed the test slope smoothly. Its 5-speed manual transmission with synchronized gears from 2nd through 5th shifted without hesitation. The Continental radial engine maintained consistent power delivery throughout the ascent despite the severe gradient. The driver, a Wehrmacht tank instructor familiar with both German and captured Allied vehicles, handled the Sherman with confidence that came from knowing the vehicle would respond predictably to control inputs. The Panther followed. Its more powerful 700 horsepower Maybach HL230 engine allowed it to match the Sherman's performance, but only barely, and with considerably more difficulty. The transmission required careful double clutching on the steep gradient. The driver avoided using third gear entirely, a deliberate choice based on field reports documenting how that particular gear ratio failed under stress. The Panther completed the climb successfully, but observers noted the caution the driver exercised and the obvious mechanical stress the vehicle experienced. The Ferdinand approached the slope with its 65 tons distributed across a chassis originally designed for a much lighter vehicle. The electric transmission system, theoretically superior to mechanical systems and representing advanced German engineering, began experiencing problems halfway up the incline. The electric motors overheated. Power delivery became erratic. The massive tank destroyer stalled completely, its engines continuing to run but unable to transmit power to the drive sprockets. Speer watched as recovery crews struggled for nearly 30 minutes to restart the vehicle and eventually had to tow it off the course using a heavy recovery vehicle. The embarrassing failure occurred before dozens of senior officers and industrial leaders who had gathered specifically to witness Germany's latest armoured fighting vehicles demonstrate their superiority over Allied designs. Instead, they watched an American tank, captured from forces that had been decisively defeated in Tunisia just months earlier, outperform Germany's newest and most expensive designs in a fundamental test of automotive capability. In his memoirs published years after the war, Speer would reflect on what he observed during inspection tours of frontline units. He noted specifically that reports on the cross-country mobility of the Sherman had been very favorable. The tank climbed mountains that German tank experts considered inaccessible to tracked vehicles. He attributed this capability to the Sherman having a very powerful motor in proportion to its weight, giving it mobility on level ground that was definitely superior to German tanks. The 26th Panzer Division had specifically documented this advantage in official reports filed from the Italian front. These observations from Germany's armaments minister carried significant weight within Wehrmacht technical circles, but they also revealed how far German understanding lagged behind the reality of American automotive engineering. The Sherman's advantage wasn't primarily about power-to-weight ratio, though that was adequate. The advantage came from a complete powertrain system that transmitted power efficiently, functioned reliably under stress, and required minimal specialized skill to operate effectively. These characteristics emerged from decades of American automotive experience that couldn't be replicated through crash programs or accelerated development timelines. A written public assessment appeared in Das Reich newspaper on June 27, 1943. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The propaganda ministry carefully controlled what German citizens learned about enemy equipment, but this article acknowledged American capabilities in terms that suggested growing respect, if not outright concern. The piece described the Sherman as one of the special point accomplishments of North American laboratories and called it quite a praiseworthy product of the North American steel industry. The article noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. It mentioned the gyro-stabilized gun sight as the first attempt of its kind ever to be made anywhere, acknowledging American innovation in fire control systems. These carefully worded public statements concealed the private alarms spreading through German engineering departments and Wehrmacht headquarters. American tanks weren't just adequate for their role, they were fundamentally better engineered for sustained field operations than anything German industry was currently producing. Back at Kummersdorf, systematic testing continued through the summer and into autumn of 1943 as engineers pushed War Daddy 3 through increasingly demanding trials. They conducted extended endurance runs that measured how many kilometers the tank could operate before requiring major component replacement. They subjected every system to stress testing designed to induce failures that would reveal design weaknesses or manufacturing defects. They compared German and American approaches to solving identical engineering challenges. The operational range testing produced results that contradicted everything German tank crews had learned to accept as normal. The Sherman documented operational ranges exceeding 2,000 kilometers before requiring major maintenance interventions such as engine overhaul or transmission rebuild. Early model Panthers, by comparison, required major maintenance after approximately 500 kilometers. Even with improvements implemented through 1943, Panther operational range barely reached 1,000 kilometers before needing factory-level repairs. The transmission efficiency measurements showed the American design, losing significantly less power between the engine flywheel and the drive sprockets compared to German transmissions. This meant more of the engine's output actually reached the tracks, improving fuel economy and reducing heat generation in the transmission housing. The synchronized manual transmission made gear changes smooth and simple, requiring neither the double clutching nor the careful rev matching that German transmissions demanded. An experienced Panther driver needed weeks of training to master the complex shifting technique that prevented damage to the straight-cut gears. An inexperienced Sherman driver could learn adequate shifting technique in hours because the helical gears and synchronizers prevented the mechanical violence that destroyed German transmissions when operators made errors. The final drives examination revealed design margins that German engineers found almost wasteful in their generosity. The American final drives used components substantially stronger than immediately necessary for the M4's 30-ton combat weight and 400 horsepower engine output. When Kummersdorf engineers calculated stress loads and compared them to component strength, they found safety factors of 2 or sometimes 3 in critical areas. German designs typically aimed for safety factors closer to 1.2, maximizing performance while minimizing weight and material consumption. The American approach seemed inefficient to engineers trained in resource-constrained design philosophy. Why use components capable of handling twice the stress they would ever encounter? The answer became apparent during sustained high-load testing. Those generous margins meant the Sherman's powertrain components operated well below their stress limits even under severe conditions. Parts wore slowly. Failures were virtually non-existent. Maintenance intervals could be extended without risking catastrophic breakdowns. German tanks, designed with minimal safety margins to save weight and scarce materials, operated near their components' stress limits during normal use. Any unexpected load, any minor manufacturing defect, any slight wear in associated parts, and catastrophic failures occurred. The theoretical efficiency of tight design margins disappeared when the practical result was vehicles breaking down and requiring repairs that took them out of service for days or weeks. Restoration projects conducted decades after the war would find Sherman final drives that needed virtually no mechanical restoration after years of storage, testament to design margins that exceeded immediate requirements by substantial factors. German final drives, by contrast, were often found with cracks in the housings, worn gears, and damaged bearings, even on vehicles that had seen relatively limited service. By late 1943, Kummersdorf had accumulated enough testing data to produce comprehensive internal reports that circulated through Wehrmacht technical branches and reached senior officers responsible for armoured force development. These documents, stamped with high classification markings and restricted to personnel with specific need-to-know clearances, painted an increasingly sobering picture of comparative capabilities that Germany's military leadership needed to understand, even as the news grew progressively worse. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite theoretical knowledge and scientific expertise that was second to none. Mass production techniques using tolerances that would be considered sloppy in German precision manufacturing somehow resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repair operations. The entire design philosophy prioritized operational availability over theoretical performance maximums. American engineers seemed to assume that any tank, no matter how impressive its specifications, was worthless if it couldn't reach the battlefield or broke down before completing its mission. German engineers had pursued maximum theoretical performance, accepting reliability compromises as inevitable trade-offs. The testing data proved that assumption wrong. Reliability wasn't a compromise against performance. It was the foundation that made performance operationally meaningful. Additional captured Shermans arrived at Kummersdorf through 1943 and 1944 as German forces seized disabled or abandoned tanks across multiple theaters. Each captured vehicle underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. The British had modified some Shermans with their 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower against heavy German armor. German engineers examined these modified tanks with particular interest, noting how the Sherman's large turret ring accommodated the significantly bigger gun with minimal structural modification. The Firefly demonstrated growth potential built into the original design that German engineers had not considered when specifying their vehicles. The Panther, rushed into production specifically to counter Soviet 34 tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions with scientific rigor. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, every maintenance requirement, every component failure or sign of impending failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern Front and in Italy, correlating laboratory testing with actual combat experience. The numbers told an unambiguous story about comparative reliability that no amount of propaganda or wishful thinking could obscure. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25% during intensive operations. Individual Panther battalions documented periods when fewer than one tank in 5 was actually capable of combat operations, the remainder sitting immobilized awaiting parts or undergoing repairs for mechanical failures. Sherman tanks, by comparison, maintained substantially higher operational availability across all theaters. American units routinely reported operational readiness rates above 70%, sometimes reaching 85 or 90% during periods when supply lines functioned normally, and maintenance units could work without enemy interference. The difference wasn't marginal. It was the difference between armored units that could execute sustained offensive operations and armored units that had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. Specific data from German field reports documented Panther reliability problems in devastating detail that senior officers could no longer dismiss as isolated incidents or teething problems with a new design. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness. Mechanical failures eliminated more tanks than Soviet anti-tank guns during the critical opening phases of the offensive. By December 1943, after months of field modifications and improved crew training, readiness had improved to only 37%. February 1944 reports showed 37% operational. April 1944 reached 50% operational. May 1944 finally achieved 78% operational readiness. This progression showed gradual improvement as the most serious design flaws were identified and corrected, but even the best Panther readiness rates never consistently matched what Shermans achieved from initial production batches in 1942. By December 1943, the pattern had become undeniable to any objective observer examining the accumulated data. Engine lifespan for Sherman diesel variants exceeded 3,000 kilometers under proper maintenance protocols. Panther engine lifespan barely reached 1,000 kilometers, even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented internally as a significant success. This improvement merely brought Panther engines to roughly one-third of Sherman diesel capability. Sherman transmissions required minimal maintenance between major overhauls, with synchronized gears that made driver error less likely to cause catastrophic damage. Panther transmissions demanded constant attention and frequent repair, with third-gear failures so common that experienced drivers learned to skip from second gear directly to fourth gear to avoid using the problematic ratio entirely. Field manuals eventually included explicit warnings about third gear usage, acknowledging a fundamental design flaw that couldn't be corrected without complete transmission redesign. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. The comparison wasn't subtle or debatable. It was measurable, documented, and impossible to explain away through appeals to different operational conditions or tactical employment. American automotive engineering simply worked better than German automotive engineering when applied to tracked armored vehicles operating under combat stress. Field reports from German units using captured Shermans reinforced the Kummersdorf testing data with real-world operational experience that carried particular credibility among frontline commanders. German mechanized units, desperate for reliable vehicles as their own tank inventory degraded through combat losses and mechanical attrition, eagerly employed any captured American tanks they could obtain intact and operational. Unlike Soviet 34 tanks, which Germans extensively modified before placing into service, Shermans entered German operational use without significant changes. They didn't require modification because they worked correctly as originally designed, with no fundamental flaws that needed correction before field employment. German tank crews, who had experienced multiple mechanical failures in their assigned vehicles, found the Sherman's reliability remarkable and frequently commented on it in letters home, after-action reports, and post-war interviews. The contrast between American and German automotive engineering became a recurring theme in these first-hand accounts. Reports from Panzer regiments noted that Sherman operators could focus their attention on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without mechanical breakdown or completing assigned missions before component failures. Immobilized their vehicles far from friendly maintenance facilities. The 10th SS Panzer Division captured 12 M4A3 Shermans at Herlisheim in January 1945 during Operation Nordwind, the final major German offensive in the West. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the initial German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war, providing German officers with extended operational experience using American equipment under actual combat conditions. These captured tanks served primarily as reconnaissance vehicles and mobile reserves, roles that required sustained movement without maintenance stops and absolutely reliable mechanical performance. German commanders recognized what Kummersdorf testing had proven years earlier through scientific measurement. American tanks could be relied upon to function when needed most. This dependability, more than firepower or armor protection, determined tactical utility in the final desperate months of the war, when German logistics had collapsed and spare parts for German vehicles were virtually non-existent. A Sherman that arrived at the battlefield with an operational 75mm gun was infinitely more valuable than a Panther with superior firepower, broken down 20 kilometers behind the front lines, waiting for replacement final drives that would never arrive. The tactical mathematics were brutally simple and completely unforgiving of theoretical superiority that couldn't be maintained in field conditions. March 1944 brought official acknowledgement from the highest levels of German Armored Force Command that Panther reliability had finally reached what General Heinz Guderian, Inspector General of Panzer Troops, termed acceptable standards. His communications to field commanders noted that engine life had reached 700 to 1,000 kilometers through improved manufacturing processes and better crew training. Final drive problems had been largely resolved through design modifications that strengthened the housing and improved gear tooth profiles. This improvement presented as significant success in German military communications and proof that German engineering had overcome initial teething problems, merely brought Panther reliability to levels that Sherman had achieved from initial production in 1942. The German army was celebrating reaching standards that American tanks had exceeded from the very beginning, highlighting how far behind German armored vehicle development had fallen, despite possessing scientific knowledge and theoretical expertise that was second to none globally. The comparison grew increasingly painful as German tank production struggled with mounting resource shortages and the devastating effects of Allied strategic bombing campaigns. The bombing targeted key bottlenecks in Panther and Tiger production chains with increasing effectiveness as Allied intelligence identified critical facilities. The Maybach engine plant in Friedrichshafen suffered catastrophic damage from Royal Air Force Bomber Command on the night of April 27 to 28, 1944. The raid involved 322 heavy bombers and is described in Imperial War Museum archives as the single most damaging attack on German tank production of the entire war. The bombing destroyed not only the engine production facilities, but also the adjacent ZF gearbox factory that produced transmissions for Panthers and Tigers. Production of tank engines and transmissions halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly from pre-bombing standards. Slave labor, increasingly employed in German tank factories, as German workers were conscripted for military service on collapsing fronts, introduced both unintentional errors and deliberate sabotage that further compromised reliability. These problems never affected Sherman production, safely located in American factories thousands of miles from any combat zone, and staffed by motivated workers earning good wages under decent conditions. The fundamental difference between American and German tank production lay not primarily in engineering knowledge, which was comparable, but in industrial capability and underlying design philosophy, shaped by decades of different experiences. German engineers understood automotive principles as thoroughly as their American counterparts, possessing extensive theoretical knowledge backed by world-class universities and research institutions. They simply never applied those principles consistently to tank design, instead prioritizing factors that produced impressive specifications but poor reliability in sustained field operations. German tanks emphasized performance characteristics that made for formidable technical documentation. The Panther's powerful 75mm KBUK 42 gun and thick frontal armor came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's 45-ton weight through its extended operations. American engineers, trained in automotive mass production through decades of civilian industry experience with millions of vehicles, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned servicing civilian automobiles and trucks. The Sherman powertrain used components proven in commercial service, with design principles borrowed directly from automobile and truck manufacturing, where reliability determined customer satisfaction and repeat sales. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality continued degrading, and spare parts became increasingly scarce due to transportation network disruption. Panthers required transport by rail for movements exceeding 100 kilometers because sustained road marches destroyed their final drives with depressing regularity. Field commands issued explicit orders restricting Panther movement to preserve the vehicles for actual combat rather than losing them to preventable mechanical failure during approach marches to the front. The Berge Panther recovery vehicle, built on a Panther chassis specifically to recover disabled Panthers, shared the same fundamental reliability problems as the combat tank it was designed to rescue. German commanders faced grim operational reality, where mechanical failures eliminated more tanks than enemy action, with some units reporting that 70% of total tank losses resulted from breakdowns rather than combat damage. Meanwhile, Sherman production continued at unprecedented rates that German industry could never approach even theoretically. American factories produced 49,324 Sherman tanks during the war, exceeding all German tank production of all types combined. British Commonwealth forces received thousands through Lend-Lease agreements. The Soviet Union received over 4,000 diesel variants that proved particularly effective on the Eastern Front. Every theatre where Sherman served confirmed what Kummersdorf testing had revealed through scientific measurement. Properly maintained, Shermans kept running under conditions that would disable or destroy German tanks with frustrating predictability. January 23, 1945, brought the final official admission of comprehensive German automotive failure. A meeting of the Panzer Commission produced a devastating report documenting catastrophic final drive failures across all German tank types currently in service. The document's findings painted a picture of systemic collapse. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in Panzer Mark IV tanks, 370 in Panthers, roughly 100 in Tigers, and approximately 200 failures in Hetzer tank destroyers based on the Czech 38-ton chassis. General Wolfgang Thomall, serving as Chief of Staff to the Inspector General of Panzer Troops under Guderian, explained the operational impact in stark terms that acknowledged what frontline commanders had been reporting for months. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles, and in some situations abandoned functioning tanks just because of final drive problems, fearing they would become stranded behind enemy lines and captured when the inevitable mechanical failure occurred. German tanks, built to intimidate through impressive technical specifications and fearsome reputations, were failing the most fundamental requirement of armoured vehicles. They couldn't reliably reach the battlefield and complete their assigned missions without breaking down. All the theoretical advantages in gun power and armour thickness became strategically meaningless when vehicles couldn't be counted on to function when needed most. The story of War Daddy 3 and the dozens of other Shermans tested exhaustively at Kummersdorf represents one of the great industrial disparities of the Second World War. German engineers, working within an industrial system that prioritized theoretical perfection over practical utility and elegant engineering over robust reliability, produced tanks that looked magnificent on paper but failed consistently in sustained field operations. American engineers, applying decades of automotive manufacturing experience gained through civilian industry competition, produced tanks that lacked technical sophistication in many areas but worked reliably under conditions that defeated German equipment with depressing regularity. In armoured warfare, as in most military operations throughout history, the weapon that functions when needed defeats the weapon that might be theoretically superior if only it could reach the battlefield and complete its mission without mechanical failure. The Sherman tank didn't win the war through technical superiority in firepower or armour protection. It won through industrial superiority expressed as mechanical reliability, consistent operational availability, and ease of maintenance that kept vehicles in action rather than in repair depots. German engineers at Kummersdorf understood this by mid-1943 based on exhaustive testing conducted with scientific rigor. They wrote detailed reports documenting their findings with professional thoroughness. They reached correct conclusions about American advantages and German shortcomings. But understanding a problem and solving it are fundamentally different challenges requiring different resources. German industry lacked the capacity to retool production around reliability-focused principles, while simultaneously fighting a losing war on multiple fronts against enemies with vastly superior combined resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and peacetime development, then simply extended those mature principles to military production with remarkable success that German industry could observe but never replicate under wartime constraints. War Daddy 3, that single Sherman tank captured in Tunisia and tested exhaustively at Kummersdorf for over a year, told an entire story through its mechanical reliability and consistent performance that contradicted German assumptions. Every kilometre it drove without failure was evidence that German tank design had taken a fundamentally flawed path. Every test that demonstrated American automotive excellence proved that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations or impressive technical specifications. The tank itself was unremarkable in many ways, just one of 49,000 produced. What it represented was devastating to German confidence. It was tangible proof that Germany had already lost the industrial war, even as fighting continued, and that American productive capacity simply could not be matched regardless of German technical sophistication, tactical skill, or soldier courage. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.